Okay, so what I'm about to talk about is basically a literature review of how we make music with AI. So let me just show you quickly what the synopsis is for this presentation. So firstly, um, we all like music. But we need to define what music is. And then we also need to figure out why we like it. Because for an AI to make good music or music that is likable, at least, we need to kind of understand the domain a bit. So I'll talk a bit about that. Then I'll talk a bit about the history of AI in music generation. Apparently has a very long history, which surprised me. And I'll talk about the state of the art music tools that musicians use a bit. And then I'll go into some of the more state of the art methods right now that we can use, which is basically using GANs for music content generation. And then I briefly discuss how we can possibly use AI to generate soca. Okay. All right. So, firstly, what exactly is music? So, music is defined, and this is like copy and pasted from Wikipedia actually, is basically the art of arranging sounds or organized sound in some definitions in time to produce composition through the elements of melody, harmony, rhythm, and timbre. So, it's kind of the generic definition of music. But what we should know is that music is transcendent, meaning that all human cultures, and as far back as anthropologists can look, have some of appreciation and composition of music, which is quite remarkable. Which means that it's kind of built in into our brains or ingrained that we have a love of music and we have a love of creating and generating music. So let's talk a bit about the philosophy of music. Now, I'm not going to delve into these six, seven questions here, but firstly, in order for an AI to make music, it needs to understand what music is. So, what separates just some random noise from music? So, I'll talk a bit about that later on. But these are some interesting questions we can think about from a philosophical perspective, because what is this is just generally the top questions that philosophers ask, like what is the relationship between music and mind? What's the music's relationship to our language? Like, do different languages shape the type of music the culture creates? Also, did music shape our evolution, or is it like vice versa? Um, Also, what does the history of music say about humanity and civilization? And why does certain music evoke the same emotions across all cultures? Like an example you can think about is like um, theme music used in horror movies that kind of build up suspense and create some anxiety and dread. That that feeling you feel when you listen to that music is universal. All humans, basically from any part of the world, will feel generally the same thing, unless that person is a bit weird, but that's okay. Lastly, we can think about is music appreciation subjective, and also what makes a piece of music good. So we'll only look at basically these two things: what separates music from noise, and what makes a piece of music good. So I'm not going to go into too much detail, but that is basically what an AI that is generating music needs to basically solve. So let's talk about why we like music. So for AI to basically create music, it needs to understand what makes a piece of music good. And we need to understand what music is. So this is where I'm going to go into a bit of music theory. I'm not going to spend too much time here, but this is just to educate some of you if you don't know much music theory, and I don't know much music theory. Just have to recap a bit of this. So basically, let's talk about our hearing or audio. Audio is basically just a sound vibration that propagates an acoustic wave, and then we hear that wave vibrations um, with our ears. Okay. So human hearing is tuned to these frequencies here, 20 hertz to 20,000 hertz. This is just a sample of what that range is. That actually isn't the exact range, but it's just a subset of that range. And music now, what we call music, is made up of 12 notes. And those 12 notes, basically, this is an example of one octave of frequencies here. And there's a formula to derive the frequencies for each note. You can see it on a piano grid here and here, the notes as well, and the frequencies of A here, and A here as we go up the octaves. So these are the 12 musical notes that we should all be familiar with. Okay, we've all probably messed with the piano and just did that. Oh, wait, why is that playing again? Sorry. So now let's talk about music scales, because music scales are generally what we interpret as sounding good. So a music scale basically is just seven notes, seven unique notes, with the eighth note being on the same beginning note, just on the higher octave. So this is what the major scale sounds like. And now the major scale is probably the most popular scale used in Western music. Sorry, let me just start this at the beginning. Keep moving it. Okay, so notice there was a pause between the last note and the second to last note. I intentionally put that pause in there just because I wanted you to think about that you pretty much knew what that note would be. But because our brain actually kind of does some sort of predictive estimation or forecasting of what that note should be based on either whether it's
Um,
natural, I'm not sure.
hey, Rajeev, I
Yeah.
don't know if anyone else heard it, but I totally didn't.
Oh, sorry. Did anyone else hear that, by the way?
I
I
could be
did.
deaf.
Yeah, I hit it.
I heard
What?
it too.
Yeah, yeah.
Torian, it's you again. Sorry.
No, no, you cannot blame Silicon Valley Internet for that. But go ahead, keep going.
Yeah, I'll figure out a way you can hear it after Torian. Anyhow, so there, that's just basically the scale there. So I just want to show you some sample of some music that we all know that is built on the major scale. I think we all know this song. And also popular pop music like the Beatles was built on a major scale. And team songs like this. Notice this one spans a few octaves here as well. So why do we like it? Now, I'm just not going to go too deep into this because there are a couple interesting TED Talks about this and a lot of research as well. But generally, listening to music you like creates dopamine, which makes us happy. But we scientists actually don't know why that happens. Like it's a mystery as to why we actually enjoy music. And there are some theories. Now, this is a quote from a neuroscientist who researches music. Basically, he's saying that C or C sharp is very rarely a matter of life and death. So it's true. So we don't know why we evolved to like music, but where was that coming from? Oh, here. Sorry. Yeah. So the theories on why we love music are basically, firstly, our brains love patterns, and that's why I was playing this. I'll play it again for you shortly. But musical notes are patterns, and generally our brains are just really, really good at just pattern recognition and finding patterns out there. So music might be a form of that. And it's actually been proven that the most likable songs are the ones that we could kind of estimate or predict what's coming next in the song, whether it's like a short term, like the next note or the next couple notes. But it's basically that pattern that our brain likes. So that's a very interesting theory, and I tend to agree with it. Um, However, there are more theories as well. One of them, well, this is not a theory, this is actually proven too, that music triggers parts of the brain that are tuned for speech, which is why different types of music can evoke different emotions. Also, it's been proven too that we do enjoy music more when it's in a communal setting. So that emotional association with hearing a piece of music with friends apparently increases your likeness or your appreciation of the music, which is probably why concerts and clubs are so popular as well. And also, there is personality and culture do shape our music appreciation. And I'll just quickly go into a study done by Cambridge University that showed they basically separated three personality types and showed that they like different types of music. But I wanted to just play this scale again. Sorry, this is scale. Sorry, and just to show you that your brain was naturally trying to predict the last note, but because the pause was there, it feels off. So you can hear it again. I think everyone will hear it except Torian, unfortunately. Yeah. So you see, your brain was actually going to predict that last note, and it wasn't there. It was a small gap. So this is the Cambridge study, the results of it here. So they separated personality types into three. There were emphatic, people who liked systems and rules, and people who were both. And they found that people who are emphatic tend to like emotional songs, sad music, soft rock, and vocal based music, which apparently also produces prolactin and oxytocin, which induces feelings of calm and relaxation. And people who like System and Rules tend to like, interestingly enough, heavy metal and classical music, which I didn't expect those two to go together, but kind of makes sense. And people who liked both, kind of like me, liked all genres of music. So it's just there for fun, I guess. So now we need to talk about, why is generating music so hard? Well, it involves a wide range of notes, there's a wide set of octaves, because a piano has like 88 keys. That's a good few octaves there. Um, a song is also comprised, like a real song is comprised of several different instruments. Then there's like the different time signatures, and different notes are stressed differently, sustain, volume. Lots of variations there that make something, that take something that sounds flat to making it sound good. So there's a lot of work that goes into making music sound good, but we still can't really figure out why it sounds good to us. We just know we like it. Could be the patenting. Also, music composition is hard for humans. That's why there's so good, little few good composers out there. So now I'm just going to delve into the history of AI in music. So apparently it starts back in 1957, which this mathematician and this composer programmed the ILAC, which was a supercomputer back then, to generate compositional material. This is actually a sample of it. Let me just fast forward it. Yeah, so it doesn't sound great, but it's like a very good start for 1957 technology. Also in 1960, some Russian researcher named RKH Zarabov published a paper on algorithmic description of the process of musical composition. I haven't actually looked at it, but could be quite interesting. Ray Kurzweil also generated a piano piece in 1965 using pattern recognition of various musical compositions. Pretty cool as well. Then in 1975, MIT formed an experimental music studio called the EMS, and they published Machine Perception of Musical Rhythm. This inferred tempo and note duration from hearing a musician play. I have A twice here for some reason. Um, and an acoustic keyboard. So you can see a quick demo of it here.
Capable of down to small milliseconds, and evolution of timbres to bringing his.
This is it here.
In bringing pieces like this to the concert stage, the MIT studio is expanding the sounds and the concepts of music by bringing professional performers and composers into a more direct contact with new emerging technologies.
So yeah, they did a lot of work in that research group. And then in the 1980s, some early generative models, I don't think these are the same generative models that we speak about now, like with GANs as generative adversarial models. What they did, we basically created a system that analyzed existing music and created new pieces from them. It's a sample here, but I wouldn't play it for you now because I know it's a little late, and I'll save some of the later stuff to play for you guys. Then in the 80s and 90s and early 2000s, when these things started to evolve to basically a better level that was acceptable in pop music, popular artists like David Bowie used AI tools to assist with music composition. Sony had a pretty successful group in Paris that created over 30 patents in audio feature extraction and music interaction. And then in 2002, they developed this program called the Continuator, which I'll play this clip for you because it's interesting, which could interactively play with a musician while performing live. So let's take a look at this. Yeah, you can watch from here. And then it continues the song afterward. So it's not perfect, but it actually was pretty good. Then in 2009, there was some actually full albums that were created from AI generated music. This one was based on, this one's called Light from Darkness Light. It was based on latent semantic analysis, and it builds its own music from a source database. Also, similarly, Sony did one called Daddy's Car, which I can play shortly here for you, which was it basically took a database of different songs and combined small elements. And a lot of these songs were from Beatles. So I'll just play like 20 seconds, 10 seconds for you guys. So that's pretty good for AI. I mean, this one is it's still in a way it is unique and new music. However, there's still a lot of debate whether if taking existing compositions and combining them in new ways is original. But then again, that's what a lot of human composers tend to do. So I guess AI can get away with it. So then IBM Watson joined in, and a few more AI albums were created. American Idol star Taryn Southern, she released an album called I Am AI, and basically all the melodies were produced by AI in it, and it's in accordance with the genre and mood. I'm not sure how they actually worked. Bjork actually did something with Microsoft as well, and produced this song which was based on changing weather patterns and position of the sun, which could be sounds a bit gimmicky, but could be cool too. So yeah, I'm just going to go over quickly some of the state-of-the-art tools used today. I wouldn't mention all because I know it's quite late and I wouldn't go into these, but these are a list of all the current tools, and there are probably a couple others out there because I kept finding a lot more actually, but these are the most popular ones.
Or Rajeev,
Yeah.
take your time. I mean, I'm sure everybody's interested, so take your
Sorry.
time. Don't worry
Yeah,
about
yeah.
it. Okay.
Okay, sure. Thanks,
Yeah.
Prof. Yeah. Well, I didn't really want to spend too much time on the slide because it was just like a list of different things, and I didn't actually know what most of them do. I just kind of like pulled out what each one was and what it was doing. MuseNet seemed interesting to me. I listened to the composition and it was quite good. What I want to learn more about is the AWS Deep Composer, which apparently comes with a 32-key 2-octave keyboard and is designed to assist the creation of new melodies. I think it's something like the Sony continuator, where you probably play something and it continues the track for you, giving you ideas or inspiration for composers. So it could be quite helpful in creating new music. Also, this site Brain FM does AI generated musical compositions for for whatever mood you want. So if you want to focus, it'll just generate all new. It's all instrumental though, by the way. This AI generated stuff. So it's pretty cool. There's a lot of stuff out there which I didn't realize anyway. So what I want to talk more about now is using generative adversarial networks for music generation. So I took a look at these three here, MuseGAN, WaveGAN, and GANSynth. Now, MuseGAN is very good. It generates MIDI music. WaveGAN was basically the genesis of using GANs to generate wave files, or I guess audio waveforms. I just spelled something wrong here, but that's okay. And GANSynth was actually an improvement of WaveGAN. So let's talk about these two as well. So firstly, what are generative adversarial networks? Well, I did a presentation a few months ago on this, but for those of you who don't remember, basically you have two neural networks, generator and a discriminator. And what the generator does, it generates, well, in this example, I'm using images here. It generates fake images from this noise here. Basically encodes it and creates a fake image. And then it feeds this, it combines this with real images here. And now the discriminator it's basically doing a loss function, trying to figure out which one is real or fake. And that's basically how it learns. So if the discriminator was correct, basically it goes back into the training mode. It just uses this information here to keep retraining over and over. So what happens over time is that both the generator and the discriminator get very good. The generator gets very good at creating fake images, and the discriminator gets very good at detecting fake images. So as you imagine, if you build up a generator here that is able to create fake images that plausibly came from a real image data set here, then you can train a neural net to take a sample of data that you have and create new samples out of it, and it should look like it just came from the same data set, which is a good way of augmenting data sets or doing lots of cool things with these generator networks like music generation, because that's what we're going to take a look at here. So if we have a data set of music and we want to basically train a GAN to create new music, it's basically effectively what we're doing here. So MuseGAN is a MIDI generating algorithm GAN that was basically published in 2008. And what it did, I won't go into too much detail here because I myself honestly don't understand fully what those guys did, but they basically they separated the lead sheet arrangement, that's the music sheet arrangement here, into two parts. Now, actually, before I begin, for those of you who don't know what MIDI files are just a digital file format for storing music notes. So we have sheet music here, and that can also be interpreted by a computer in a MIDI file. So everything, imagine you have a keyboard, a digital keyboard, everything you play there can be transcribed either digitally like this, or you can actually do it with music notation like this. So what this is doing is generating basically computer instructions for how to play this music. So it's not actually doing a wave file. Wave file would be like me talking right now. That's like a wave file. It's like a analog type file if you want to consider analog, but it's actually digital too in this case. But this is more instrumental here. So what MuseGAN did, was that it separated the lead sheet arrangement into two parts: the unconditioned generation model that generates lead sheets from nothing, and then the conditioned generation model that takes lead sheets as input and then generates the arrangement. So in the first stage, the lead generation, they shrunk the number of tracks to 2, melody and chord, and in the second stage, which is the here, lead sheet arrangement, MuseGAN learns to generate 5 tracks of instruments. So we can take a look here. This is the arrangement here for the architecture of how it worked. And this was supposed to be a sample, but it's not loading for some reason. Hopefully afterward it will load. I'll probably refresh the presentation after. So now let's move on to WaveGAN. Now WaveGAN was basically a big pioneer in GANs in terms of generating audio files. So the approach was, because DC GAN was a very popular image generator that came out, I think, the year or two before. And what they wanted to do was to convert audio files into a way that DC GAN could sort of like interpret the encodings in that data set, in that file, and generate new ones out of it. So just to quickly talk about how you represent audio data as digital files. Basically, imagine this is like a piece of a song here. And every second, you take 44,100 samples per second. And you basically encode it 16 bits here. It's the amplitude here. You're encoding. So it's 65 range values, 65,000 range values here. So that's what they converted audio files to. That's the WaveGAN sample here. You'll hear that afterward. So yeah, so what made WaveGAN possible was that they observed that there were correlations across large windows seen in audio files. And as such, they adjusted the receptor fields to be larger to process the raw audio. And once processed in this form, they were able to use that format for the DC GAN algorithm and generate spectrographs as waveforms like this here. So this is some of the stuff I took from the paper. And the accuracy of the discriminator in the end for this network was 66%, which was quite good, which means that the generator was generating stuff pretty high quality at that point. So you can take a listen to the samples here. Yeah, just so you know, these are all like really like short clips that they kind of like put together in one file, like 3-4 second clips. But all of this is generated by the GAN. So it's all technically original content, even though it sounds super original, but it is all generated from this GAN. So it's quite good. So now GAN synth was, that's not even supposed to be here. That's okay. Yeah, GAN was an improvement over WaveGAN, sorry. And what it did, basically, rather than generate audio sequentially, Ganson generates the entire sequence in parallel. So it was 50,000, sorry, times faster than the standard WaveNet on a modern GPU, which is incredible. But it's just they took a different approach on how to do basically the same thing. And unlike WaveNet, which use autoencoders, what they did basically, Ganson generates the entire audio clip from a single latent vector, allowing for easier detanglement of global features such as pitch and timbre. And I'll take a look at some slides here to show you what or how Gansint actually works. So Gansint uses something called progressive GAN architecture, which you can probably have an hour-long video on explaining this as well, but we won't get into too much here. But what it does, it incrementally upsample from with convolution from a single vector to the full sound. So previous work had difficulty generating coherent waveforms because upsampling convolutions struggle with phase alignment for highly periodic signals. And this is an example of the periodic alignment issue that they would have. So the red or yellow curve is a periodic signal, and the black dot denotes the start of each wave. So as you can see over time, it's basically starting to shift and go off course. So for strided convolutions, this requires a convolution to learn all phases to fix this, which is very computationally inefficient. So Ganson solved this by basically exploiting the periodicity observed in music. So this is a phase here. As you can see, it goes up and down, periodic like this. What they did, they basically unwrap it like this here, left it with a constant amount here in each frame, increases by a constant amount, sorry. And this is the instantaneous frequency here of each one. And they did something called the short time Fourier transform, SDFT. And basically what that does, it compares a frame of signal to many different frequencies that leads to the speckled patterns here. And just so you know what SDFT is a Fourier transform to determine the sinusoidal frequency and phase content of local sections of signal as it changes over time. So, I mean, I should know all this in my signal processing course, but kind of forgot all that theory. Prof might know a lot more about this stuff. But anyway, so however, when the instantaneous frequencies was extracted, they saw bold consistent lines here. You can see them right here that reflected in coherent periodicity of the underlying song. So now you can see here a quick sample of what Gansint produced, and it's actually quite good. So it's probably the best and highest quality AI synthesis of waveforms so far. So now let's take a look at two ways we can probably make some AI generated soca, which would be the next step in this project that I'm thinking about. So there are two ways we can do this. One, we can convert hundreds of soca songs to MIDI. There are ways we can do this. It might be messy, so we'll need to separate tracks probably properly into bass, drums, and accompaniments, and then use MuseGAN to generate a MIDI file of that soca. Now it's gonna sound like not like real soca. It's going to just be a MIDI version of it, but it could be used to inspire an artist to basically someone like Travis Will to produce the actual track and then get somebody to sing on top of it. And maybe if we have some AI generated soca lyrics, we can make a fully AI song. Might be cool. That's basically directed to Nydia for her stuff. And secondly, we can use Gansint. Now, Gansint would require us to basically break up hundreds of soca songs into smaller chunks. So we have complete bars, verses, or choruses if they're short enough, and train them on some GPUs with Gansint here. And we'll probably have some AI generated cool little soca waveform going, hopefully. So that's it for this presentation. If you have any questions, let me know.
No, very interesting stuff, Rajeev. I have no specific question, but the last one you played, yeah, it sounded a little better, but I'm surprised the quality still isn't as good as you would think it should be at, at this point in time, right?
Yeah. Well, early on, what was happening was that they were generating more like MIDI files out of it, and then it's getting professional musicians to play on top of it. So you wouldn't know how bad it sounded, but it was
Yeah.
basically just to produce the music notes, and someone would take it from there.
Okay. Yeah, but no, interesting stuff. Thanks.
Sure, Prof. Anyone else?
Okay, I guess if there are more questions, let's thank Rajeev for his presentation.
Sure, no problem, guys.
So Rajeev, by next presentation, you'll have samples for us?
I hope so. I mean, I learned the process how to do it. It's easier with Musgan, but I have to get the MIDI files for the soca.
Yeah.
Yeah, using Gansint, if I could get the stems, which would be like the pieces of soca broken down into small bits, could probably try with that too. But it is definitely possible. And the code for these things is there on GitHub. You just need the GPUs to run it, basically.
Yeah, I mean, I don't know. I mean, just off the top of my head, somehow I think there's probably a better way to do it. You know, kind of layering stuff one on top. You know, you start with just the basic stuff you would hum in hum in your head, and then you add instrumentation up on top of that. But I can't figure out a way you would do something like that instead of just taking the entire thing and trying to replicate it together. But
I think
would be like using the stems,
yeah,
like maybe just like, because you know sometimes when you listen to the stems, like a piece of it, like a layer, it sounds nothing like the song because it's so simple.
yeah, that's true.
Right, and then you just add stuff on that, especially with soca, right? There's just the basic the beat stuff, and then you have this the intermittent stuff that you put in, but you have it not only periodic, but you have these breaks in it, etc. And then you add to it in some form or fashion. But I mean, I don't have a good grasp as to how to do.
No, but it's a good thing you bring it up because not much people have mentioned like the layering aspect of music. They kind of just go with the basics and generate it from there, or just take wave files and generate it from there. That same Gansint and WaveGAN, they use that to do the human synthesis speech a lot. So like those that have human sounding voices, those were based on those GANs too, a lot of them.
Okay, but yeah, I see a lot of room for improvement in this area at least.
Yeah, I think there is. Yeah.
Maybe you could just use the like, you know, in this time they have like just the percussion like this, but not the full percussion, the simple one. You could maybe try it with that first, because it's yeah,
that could be a good idea actually, because you could separate the drumming tracks from a song and then use that alone to generate something.
Right, and you know, you still need to bridge the layers, but the layers could kind of be independent, and then you find a way to bridge them, and add one on top of the other. Yeah, as Nydia pointed out, percussion, and then you add, you know, strings, etc. But
no, exactly.
Is it free to get the local stems for the soca?
I don't know. We know some people who could give us though, so we could ask them.
Yeah, that guy. Okay, yeah, because if you can get it, that would save you a lot of work.
Yeah. And then if, as Prof was saying, that the GANs and stuff, there are a lot of room for improvement in them. So perhaps we could take a look and see if there's anything novel we can do. Or at least maybe make it more appropriate for soca too, if there's anything.
Yeah, I mean, one thing with soca, I mean, you know, compared to so like if you compare with classical music, is much simpler, right? So
yeah.
So hopefully we could do something with it. Yeah.
Yeah, no, I'm definitely gonna try, for sure. It'll be a fun project to do.